Okay, so we're going to start on the chapter 9. Chapter 9 is the first chapter of chemical bonding. So in this chapter, we are mainly going to study the Lewis bonding theory. Alright, so sometimes we are wondering why atoms bond. And chemical bonds produce or form because they lower the potential energy between the charged particles that compose the atoms. And a chemical bond forms when the potential energy of the bonded atom is less than the potential energy of the separated atoms. To calculate this potential energy, we need to consider the following interactions. We need to consider the nuclear-to-nuclear repulsions. We need to consider the electron-to-electron repulsions. And we need to consider the nucleus to the electron attractions. For example, you can calculate kind of relatively easy the total potential energy for the H2 molecules. And you can see as this curve will indicate. And this axis is about the total energy of two H atoms. And this axis, the horizontal axis, is the distance between the two atoms or between the two nuclei. Right, so let's starting from this side, when the two H atoms are kind of far away, and we have two free atoms. And then we have this much of energy, and we assign them, if they are really far away, the energy, these two together is 0. And then as we bring them together, so that means this axis, this number getting smaller and smaller, and we see this red curve, the total energy of these two together getting lower and lower. Okay, so now it's reaching a lowest point. After the lowest point, if these two atoms are getting more closer and closer, the repulsion between the electron, and then the repulsion between, especially the repulsion between the nuclear and nuclear, that becomes important, and the total energy increases. But at least we find out from this one simple example, so there is one optimal or a best distance between the two nuclei, and this distance is related to the chemical bond length between these two H atoms. So this is a very good example, and it shows us. So there are really some of those atoms when they bond together, the energy is lower. So this is the reason a lot of atoms bonding together produce molecular. Right. So then, depending on where are those electrons between the two atoms, and we have some of those terminologies, the so-called types of chemical bond. So usually there is not a really sharp cutting line between those categories. We use them as those kind of milestones and help us to understand. Right, so it's better as you study more and more in details, and so this table will not tell you always true. In general, these are true. We will see like what type of bond depends on what type of atom bonding together. And then we know those atoms are organized in the periodic table. And roughly you can see there are some of those metal atom, non-metal atom. Even though in the middle you have those metalloids. Right. So then we will approximately see whenever the metals bond into the non-metals, and we will have the ionic bond. The characteristic of ionic bond is the electron transferred completely. And that is true for some of those metals with non-metals, but not always true for or between any metal, between any non-metals. A very good example of a non-metal is carbon. And carbon, as we studied in this chapter, has the electronegativity is right in the middle, about 2.4. And so then, when you have those carbon bonding to those metals, usually they will not produce those ionic bonds, which means carbon is not strong enough to grab all the electrons from the metals. But as I said, you can use this as a roughly guiding line. And so then the second type is between non-metal to non-metals, and we will see the covalent. Covalent by the name co means shared. So the electrons are shared. And then later on we are going to study in details how they share, how much they share. They share like 2 electrons, they share 4 electrons, they share 6 electrons. And when they share, which one take more? Or do we take like divide evenly? Right? So then there's also like metals to non-metals, metal to metals. And metal to non-metal we will see in the first one. And then non-metal to non-metal in the second one. Then the last one I'm going to think about is between metal and metals. Between metal and metals, so-called the metallic bond. A metallic bond is kind of all those metal atoms, they were donating or lose up those valence electrons and produce electron pool, electron C, like the so those are the electron C and the electron pool. So then those electrons, they can really move in freely in the material, like in like a wire of copper. So each copper will give like some number of electrons, and then those electrons are freely moving, really flexible. And then those leftover electrons and the nuclear become those cations, and they can kind of like an island floating in the water. Right? So this is roughly this 3 types. Right? But you don't like always think everyone just according to what we say. And between metal and non-metal, probably ionic, and that's very good. Very good example is there are some exceptions. Right. So this picture summarizes those different bonds have different materials. So this sodium chloride is an ionic bond, and that is a very good example. So clearly the electron is transferred. And we have sodium ion, positive ion, we have a chloride ion, negative ion. And we see that for sure because we can measure that. We know there's an ion, and how do you know there's an ion? For example, you can take some of those sodium chloride solid and you heat it up to about 900 degrees Celsius, it becomes liquid. And then you can plug into like 2 those electrodes, and you will produce, you use battery, use voltage, you will produce a complete circuit. That means the electrons or the charged particles can go through that liquid sodium chloride. So then where does charged particles come from? We know that it comes from the sodium chloride. Water is another example of the covalent bond. And we see in water, you don't have, you probably have a little bit of you study in travel, if you take chemistry 1 or 2, for pure water, you have like 10 to the -3 molar concentration of H plus and OH1 negative, which means every 2 water molecule out of like 1 billion water molecule become ion. But that is really not significant in terms of they become ions. So therefore, we consider all the water covalent bond together and is kept as an intact water molecule. But obviously, water molecule like H2 can exist as different states. You can see this is a good example of a solid state. And that means all those water molecules in good spot of lattice. And you can apply energy, and then those water molecules will have more energy. They will vibrate strongly, and then they will become liquid. So those will start in Chapter 11. So then this is another example of those metallic bonds. And this is pure metal. In pure metal, like this, for example, here is sodium. And what you can imagine is each sodium atom, as we study in Chapter 7, has one of those valence electrons in that 3s atomic orbital. Then we also learned that ionization energy for those alkali metals, group 1A, is very low. Which means you don't need too much energy to leave off that one electron from a sodium atom. Right? So when these like become together, like all those sodium atoms together, they will each of them like donating one of the electrons, the electron produce a C. And then left over those cations, together still there's some electron left over, were floating in there. Because they're floating, the metal has the characteristic. You can bend it, you can stretch it. You bend it, and that means you can change those location of those cations, and you still have all those attractions from like all everywhere. It's not like those water. Okay? So those water, they have those certain geometries, okay? And it's not that like ice. If you bend it, those intermolecular attractions become break, and you cannot not that flexible. Yeah. So that first is the ionic bond. Is when the metal, usually when the metal atom lost electrons and become cation. But as we saw in Chapter 2, there's one important intersection is a group of non-metal atoms, so they can also produce a cation. So there's more of those kind of cations that come from those non-metals, but as like the first, the first time you see those concepts, probably just see all those cations from those metals. So why that? Now we can really put all those chapters together. So we study in the previous chapters. So metal have a relatively lower ionization energy. Ionization energy is the energy required, or the energy you need to put in to take the electron away from those atoms in gas state. But even though that's in reality they're not all in gas state, but give us some of the idea how easy you can take the electron away from the atom. So it's that easy to take away, so therefore, and if you have some other atom want the electron, that can happen. So then those nonmetals usually are gain some extra electrons. And the electron has a negative charge. If you lose it, what's left over become plus. If you gain it, then altogether it becomes negative. We also talk about in the previous chapters why they do that, why they lost electron, why they gain electron. Not only because this number, the so-called ion at this energy is low or high. We also talk about in chapter 7 those electron configurations, like those quantum mechanics model. Okay? So they lost electron, or they gain electron, wanted to be like a normal gas, even though most of the atom can getting closer to the normal gas, like especially those group A elements, but those transition metals, it's very difficult for them to be like a normal gas, but they still have those tendency, try to be stable. Right, so if that happens, if you have those nonmetals strong enough, and grab the electron, become the anion, and those metal atom lost electron become cation, and then you have those fundamental attraction. The fundamental attraction is between positive electrical charge and negative electrical charge. So therefore we have the attraction between the cation and the anion. Right. Now if you have those nonmetals together, and then all those nonmetals, they are relatively not that easy to give out the electron. Oppositely, they were try to grab an electron relatively easy. So then, if you have the metal together with nonmetal, then the nonmetal can grab the electron from the metals. But when you have two nonmetals together, neither of them will easily give out the electron. So then the natural tendency is they share. They share the electrons. The reason they share electrons is also they want to be like a normal gas. So then when you share the electrons, the best way to share the electrons is right on the line that connecting the two nuclei, and that's the best one. But that do not exclude the possibility of the electron little bit above of the line, or even like moving to the other side. Those depend on when we start in chapter 7. We know the electron is undetermined. We can only see the probability of the electron most of the time is on the line, but sometimes off the line. And then also this is this just talk about between two atoms, and those kind of idea is you localize or you confine or you limitate the electron only between the two nuclei. But there's some other bonding theory will give us a better picture or give us a better matching to the experimental result when we think about the electron not only between two atoms, it's really between many atoms. So the so-called localized or delocalized. So therefore there is some other bonding theory. And there's so Lewis bonding theory is pretty much emphasized on the localized in between two atoms. Then we'll see the valence bonding theory. So valence bonding theory, they were better, they were newer than Lewis. You talk about how you produce those different geometry and different number of bonds by first you mix up those atomic orbitals. But that still have some of those limitations. Then one better theory is sort of the molecular orbital bonding theory that really put the electron in the molecular and consider all those atoms, all those nuclei, and that will be the best picture. But that is very, very, we can say a huge task in terms of theoretical calculations. Metallic bond, and as we talked about before, when you have those metals together, it's very similar when you have all those non-metals together. So neither of them will get electron that easy. They all give out electron easy. So what happened? You were collecting all those electrons and produce electron C. this metallic bond is really when it is trained of the total delocalized, so all the electron in like one like example of metal material. You can see that the electron can flow over really a distance you can see with your naked eye, even though the electron you cannot see by yourself.
Is that why metal is such a good conductor of electricity?
Yeah, that's the reason metal is a good conductor of electricity, and also very good conductor of thermal energies. You apply energy on one end of if you use like an iron rod in a fireplace, and if that end become very hot, then this end you will feel very very strong because the electron can really move in, and either they really translation or move in, or they vibrate very easily bonding, so therefore, so this picture will help us understanding the metallic bond again. So those kind of liquid electrons and those little canons floating in there. So now in the chemical bond, as we said, if you want to get a precise picture, and you want to consider all the electrons. So no matter the electron in 1s, in 2s, or in 2p, you consider all of them because all of them can give some of those influence. But usually the chemists, we said, they know it's difficult to consider all those electrons, and so they will just consider those valence electrons. So we studied in chapter 7 those electron configurations, so then we also studied how to counting out or find out how many valence electrons for like a given atom. That will depend on the type of atom. Depend on the atom in group A, group 1A, group 2A, group 3A, or those group B. Right. So in this chapter, most of the bonding is between, we talk about here, is between those group A elements. Group A element has a very good pattern and very easy to find out how many valence electrons, right? So you probably still remember, so those group A's, so the number of valence electrons that equals, very easy to find out, right? You still remember how we found out that very quick, the group number, right? Yeah, so equals the group number. For the number of group 1A, you have lithium and sodium and potassium. Then we know for each one of those atoms there is one valence electron. And group 7A, right? So we have fluorine and chlorine and bromine. Then we know for each those fluorine atom, or for each one chlorine atom, or for each one bromine atom, there are 7 valence electrons. So to know that is very, very important. And for those transition metals, okay, there are valence electron is difficult to find out. You find out the highest N, right? And then you find out those number of electrons in S. Then you find out the N minus 1D, right? So usually you will not go by those group numbers. But we are not going to study too much about those transition metal group B, right? So the first bonding theory that depend on this Lewis bonding, depend on the electrons is sort of Lewis bonding theory. He is an American chemist, I think in the California Institute of Technology. It's a very famous institute. And so he developed a theory that can explain the bonding between metal and non-metals, those ionic bond. And he can explain why like the sodium is 1 plus, and why like fluorine it will become like 1 negative. And he also can explain those ratios. So when like sodium and Cl bonding together is 1:1 ratio, but when calcium and chlorine bonding together is a 1:2 ratio. So depending on his theory, and each atom, his theory, the fundamental line, or the bottom line, is all those atoms try to be stable as normal gas. Even though there's many exceptions to that, but use that as an idea. You can explain many those common molecules, the ratios, and the geometries.
Is this the one where we start drawing them? Like,
yeah.
we'll have to show
So
them?
this is this chapter's main focus. So we are going to see, like, briefly see how we can use the Lewis bonding theory to predict the ratio between calcium and chlorine. Calcium give out 2 electrons. Each one chlorine only get one electron. So therefore, if you take calcium together with chlorine, and for each calcium atom, you need like 2 chlorine atoms to receive that 2 electrons. So you are. Go ahead.
No, I'm just looking at them because I know carbon can give off 4 bonds, right?
Carbon usually will produce 4 covalent bonds. Very good. Yeah. That's why carbon is so important, and will kind of produce its own like a branch called the organic chemistry. So you can carbon bonding to carbon, carbon bonding to oxygen, carbon bonding to hydrogen, to sulfur, to nitrogen, and produce many of those important molecular drugs, fibers, materials, clothes, and that it's really like dramatically change our life. Period of life getting longer and longer. And a lot of person, when they're getting older, depend on those, depend on the modern new drugs, and that's amazing. And how can that really fighting the Alzheimer's and fighting like the cancers and diabetes and heart disease. And then you see those material. You see you only use like the natural materials. Now you have all those different fibers. Yeah, I think there's one professor in the Northwestern University. He produced a very amazing material that was not attracting to anything. And you think about some material is hydrophobic, some material hydrophilic. So that means you can either attracting to those polar molecular or non-polar molecular. But somehow he produced something that is do not attract to anything. That means he can produce very good like a raincoat. Yeah, it's a modern technology, so he not only use those chemical bond, he also uses like new technology, like those like nanostructures, the micro. All right. So like the Lewis theory also like very important, like the chemical bond, even though it's very simple. It will like help us predicting or understanding many of the properties such as molecular stability, molecular shape, size, and polarity. Molecular stability referring to, so like when you have like H and hydrogen together, the most stable molecule is H2O, not H3O, not HO2 or something like that. Use like that Lewis bounding theory, you can predict, you can draw the Lewis structure, and then you see that makes sense. Once you have the Lewis structure, you can also understand what kind of shape they have. Shape of a molecule is very important. Right? What are these three H2O, these three atoms, is banded. That means they are not straight. So then, if you study those, that carbon chemistry, that organic chemistry, there's like three important subjects you study those organic chemistry. One is those reactivity, and one of that is geometry. So that means the shape. So, and you see that the shape of geometry is important in our own system, in our body. We know like we have those enzymes that you can either have that left side, right side, but only one enzyme works. Right, so that's about that. And Lewis theory, well, again, that is a similar theory, but emphasize on one electrons. So therefore, we first kind of review to see how we decide how many valence electrons each atom has, and how you represent that. This kind of review like what we studied in chapter 7, the so-called orbital diagram. Right? So orbital diagram, pretty much you can draw a square, a box for each electron inside all the valence. But here you only see that valence electrons. And as you know, what we study here is the group, the main group. What I mean by main group is the group A. So those A group elements has another name called the main group. And here are a few examples. Okay? And so as you know that lithium is group 1A, that means has one valence. How you represent that? You just put in like one dot on that. So then sequentially, so this guy will have 8, because that is the group 8A. How you representing those? You representing them like this. So here we are, lithium, one dot, and this one dot representing that valence electron. And we know that lithium neutral atom has 3 electrons, right? So the other 2 electrons, together with nucleus, is represented by the chemical symbol Li. Right? And as I said, they're very similar as the orbital diagram. So when you draw the orbital diagram, if you have 1 electron, you just put on one box. If you have 2 electrons, usually you will pair them up in one box, and that's because that 2 electrons will be in those S orbitals. And you adding more electrons, boron has 5, but only have 3 valence, so 1, 2, 3. Carbon has 4, so that you add in, and initially you don't pair them up, right? So that's very similar. You have that orbital diagram. All right. So that gives us a starting point, right? And we can very easily identify how many valence electrons for each one of those main group atoms. And once we have that, and we can go on to the next topic. Is about how we represent those valence electron for the ionic bond. And then we will move on to the main focus, which is about the Lewis structure. Where are those dots for those molecular compounds? So we start in chapter 1. We have matter. Matter can be pure substance, which means can be element and compound. Then we know a compound can be ionic and can be molecular. So ionic bond, this theory is relatively easy. You just know how to draw the root start structure for the canal, for the animal. And then you will learn how to draw the root structure for water, for those organic molecules, for like ethanol, for methanol, for some of those simple like methane, like the natural gas. Right. So here's a very quick practice. If you want to write the root structure for one atom, usually I will ask you to write the root structure for those group A atom. What you do is just identify if that group A is 5A or 6A. Okay? If it's 5A, that means you have 5 valence. And then how you tell that it's 5 valence electron, use dot. Here's one, this is one example. So arsenic is yes. In the sometimes we call the group of the column. So we say the column 5A. 5A, that means we have 5 valence electrons. To represent the 5, use 5 dots. So according to the convention, different books have a different convention. This book's convention is the first pair, the first two. And then the next 3 spread out on the other 3 sides. Right? So that is the root structure or the root start symbol for a simple atom. Now let's talk about for those ion or those ionic bonds. For the ions, we see the fundamental line, the bottom line is everyone want to be like a normal gas, be stable. Okay? So some of those atoms, if they are closer to neon, they will be like a neon. If they are closer to helium, they will be like helium. Right? But there are some exceptions, so you not always not always can do that. Right? So we know like between metal and non-metals, and as a first approximation, you will see that they always produce ionic bond, even though that's not always true. So pretty soon you will see in chapter 10, we're going to deny ourselves. So we'll see here we see between any metal, non-metal, ionic. Then we'll see we have to use some of those numbers, calculate whether we have that electronegativity large enough to become ionic. So if you want to take the one example, let's see that lithium and fluorine, and then we know lithium is metal and fluorine is non-metal. This is a good example. So, it's very, very kind of perfect. If you take that lithium together with fluorine, lithium will give out completely that electron, right? And to the fluorine atom. Right? So once that happens, and you will have those ions, right? And here we are. So those metals, you are lost enough electron, become the previous normal gas, and then the non-metal, you will gain enough electron to become the next normal gas. Okay? Sodium electron configuration is the neon, then plus 1 electron in the 3s1. So after this goes through some of the chemical reactions and that lost 1 electron become Na+, then the configuration become neon. That's perfect example. But in reality, a lot of atoms do not really so heavy like those good examples. Now magnesium has 2, so you lost 2 that become neon. Aluminum Al has 3 valence and lost all the 3 become neon. That's really depend on who they are reacting with. So then those non-metals, for example, oxygen has this electron configuration. I just checked this. Before I just write O2 negative, fluorine 1 negative. But to be consistent, I mean, whenever we write the electron configuration for the anion, we want to see the dot. Okay? When we write the electron configuration for the cation, we don't want to see the dot. That means they already lost all those valence. Remember, those dots representing those valence electrons. So then Lewis theory just explained the ionic bond just like that. So the metal lost electron becomes cation, non-metal gain electron becomes anion, and then obviously the negative charge and positive charge are attracting, so they will start together as a chemical bond. So then use that same idea, you can explain how many atoms do you need, how many sodium do you need, how many chlorine do you need, how many calcium do you need, and how many chlorine do you need. So again, that bottom line we talk about is like normal gas. Well, most of normal gas, except helium, has 8 valence. So therefore, people also, our like the baseline that. So how do we know what time the atom have enough electron? What time those non-metals get enough electron? So the line is like a so-called orbitat. So the orbitat is really, so I put that in the quotation marks. So it's really a rough approximation. So you use that not literally as orbitat as 8, just as some of those perfect matching like has 8. Then you also see there's a lot of exceptions. Where that 8 come from? 8 will come from that some NS2, maybe like a 2S2, and then plus those electrons that's in the P, maybe 2P. So whenever we have this S2 and P6, and you add it together, get 8. And obviously for helium, that cannot happen. For helium, we have 2. Now there are 3 types of exceptions to that 8 rule, to that octet rule. So one is those has less than 8. Those has less than 8, which means those atom has a small number of protons in it. Now how much proton we have in an atom depends on the atomic number. So the first few elements, like hydrogen and lithium, we don't talk about helium because helium is not gas, and then beryllium and borons, and even like you go on to like the next period, like this aluminum, so there's sometimes also give you some of those exceptions, and especially when you study those organic chemistry, so that become very important catalysts. Now these few, they are the kind of small atoms, so they have a small number of protons, so therefore they cannot attracting so much of electron. If you give them 80 electrons, they cannot handle that amount of 80 electron. And so they try to be like a helium. Even they try like helium, there are some exceptions. Now we'll see there are perfect examples they were like helium. Any question? We know helium has 2 valence, so we also call that a duet. So for example, lithium has 3 electrons and only 1 valence. If you lost 1 electron valence, then the next 2 electrons that is inside, initially that are called the inner, become the valence. Right? So therefore, after lithium lost 1 electron, the leftover lithium cation has 2 valence. And that matching exactly like helium. Now initially, each atom has 1 electron. And that 1 electron, you can either call that valence or not 1, but that's valence. It's only 1 electron, right? And so usually it also wants to be like a noble gas, right? And it can share electron with some other atom. Right? But there's one exception for that. Okay? That means that each atom can lose 1 electron, become H plus. Now obviously, each atom, when they share electron here, that will give you two valence electrons. But when it lost an electron become 8 plus, and that will give you 0 valence electron. I mean, already see there's one exception, right? These few atoms, they want to be like a helium, that means they want to have 2 electrons or duet. So lithium ion is okay, so have a duet. If H share electron with someone else, maybe share with oxygen, maybe share with Cl, chlorine, as long as you share electron with something else, so altogether that H will have 2 valence that also matching the duet. But very, very common, for example, this H plus is representing acid. So a lot of acid solution has the H plus. Then how many valence electrons the H plus has? 0, because there's no electron at all. So then talk about the next one, beryllium Be, and Be can also lose 2 electrons. If that lost 2 electrons, we know Be atom has 4. If you lose 2, and that give you, this will give you like 2 valence electrons. That's also matching the helium. And also very common, so that that Be will share 2 pair of electrons with some other 2 atoms, and so that means you have like a double bond, a 2 bond between the beryllium and something else. For example, you can see beryllium and Cl, and beryllium and Cl. Even though, by the way, I like deny myself. I said like whenever you have this metal and non-metal, you have ionic. But if you study that electronegativity, you will see actually the electronegativity between Cl and beryllium is not large difference enough. It's still covalent. Now covalent, that means they share electron. So beryllium share like 2 electrons with 1 Cl on the left side, and share 2 other electrons with other Cl on the right side. So altogether, in the vicinity, or in the nearby of this beryllium atom, we have 4 electrons. Right? 4 electrons, obviously that's not a duet. That's not the exception. So 4 valence. So this means we have 4 valence electrons. So the last one is boron, right? Boron, let's see, like if it lost all the 3 electrons, lost all the 3 valence, it becomes 3 plus. Initially, boron has 5. If you lost 3, you can have 2 left over, and that becomes duet. So this is a duet. So that's good. So we have 2 valence electrons. But boron can also share with 3 atoms. Yeah.
Sorry to interrupt the lesson. Are we doing a lab today by any chance?
Today we do the lab, a kind of dry lab. So,
Dry lab?
Yeah. So we just the molecular geometry.
You're just drawing loose cell structures.
Yeah.
Oh, we're not gonna be, do we have to do a lab report over it, or?
We do the lab report, right? We do lab report.
We don't actually go to the lab though?
Yeah, I would like give you some of those molecular model set.
Are you talking about those ones that you can like attach?
Yeah.
Oh, yeah, I know what
You
you're
have you have those.
The
stick.
yellow, the blue,
Yeah, yeah.
the red, you gotta put them together, the black for carbon, right?
Yeah. So the boron is all very typical. So sometimes it lost 3 electrons, become 3 plus, but a lot of time that will share like 3 pair of electrons with other 3 atoms. And so that is 6 valence electrons. now you can see those, all the few possibilities, right? So we have two electrons, that's typical for the duet. And we have a 0 valence. And we have 4 valence. And we have a 6 valence. All the possibilities. 0 and 2 and 4 and 6, all those numbers. Right? And octet, to put that in the position mark, that means 8. Right? Now all these few exceptions, 0, 2, 4, 6, not 8. Right? So if they are not 8, we still got exceptions. So some atoms, if they are large enough, right, that means how large they are not enough, well, roughly not enough. I think that's most of the chemists agree. Right? That means in period 3 and below. Right? So who is in period 3? You can see Al, silicon, phosphorus, and sulfur. So typically, you will start with phosphorus and sulfur. Yeah, so a lot of chemists, I think they explain this fundamental rule and find out a very, very important material. Catalyst, a new way of synthetic chemistry. And some of them even like invented some of those new reagents and Nobel Prize. And so there are some of those fundamentals involved. So period 3 and below, if you have those atoms as the center atom in the middle, and they can have more than 8. Now what do you think? So we have more than 8. So that means we can have this number. That means you can have 10, and you can have 12. And that's always common. Or you can have 14, but that's too much. Right? So you have 12, then you have a 6 pair. So that's what the maximum we consider in this few chapters. And so you probably wonder, why only those exceptions? Why only like 0, 2, 4, 6, only those even numbers? Is it possible for those odd numbers? Right? Yeah, you don't have to pay, right? What happens if you have odd numbers? It's possible that some of those atoms give you odd number of valence electrons, right? Like one nitrogen atom have how many valence electrons? 5. So this is 5 valence electrons. And then if you pair this one oxygen with, you pair out this with one oxygen, and how many valence electrons oxygen gives to you? 6. So you add them together, and adding all together, how many valences you have?
Well, it's going to be a double bond, isn't it?
You can, no matter double bond, triple bond, you can probably a triple bond, double bond. No matter double bond, triple bond you have, but one atom will have odd number. Right? So this is what our other exception. Right? So this is what our other exception. And that means we really have some of those molecular, that has some of the molecular is very, very complicated, and some of the molecular is very simple. But if you add in together all what is the total number of valence, if you have a number, and then no matter what you do, you give that 8, and then you have a 3 left over, right? You have total 11, right? So you are not to have octet. Right, so that's the that view. So what we want to remember from the last slide is octet rule. And then we also know there's 3 important exceptions, right? So the small atom has less than octet, large atom has more than octet, and then some of those atoms, or some of those molecular has odd numbers. Right. Now we go back to like say that the electron transfer and what are the ratios. Right. Lithium, as indicated by this electron configuration, has this one valence, and that's really easy to take away. So if you have a fluorine atom, fluorine atom has a very large effective nuclear charge, which means any one of these 7 dots is attracted approximately by 7 plus each one of them, because all these 7 here, they kind of like standing like in a on the outside, and so they were not screening, blocking each other. So therefore, loss any one of this is not easy. And that one dot in lithium is only attracted by 1 plus.
And there's 1 negative.
1 negative, 1 plus. So that's the attraction.
Put them together.
And here is 1 negative 7 plus. So you get 7 times different at least.
Octet rule, put them together.
So you want to be stable like normal gas. So what do? You either share electron. If you have the ability, you have to have enough proton to attracting that electron you're going to share. For lithium, there's only 3 plus in the nucleus. So when it comes together with fluorine, fluorine just like the line share. So that will grab the electron away. And whatever over lithium will become plus, and fluorine will have all together has now have 8 dots. And this is the symbol for the fluoride ion, and then the symbol, you don't have to use variegated, just the chemical symbol for lithium Li, 1 plus. For the negative ion, you still want to show your valence electron. Even though that lithium, you take that over, it's also have valence, but that is the new valence, kind of the inner valence. And this is still the initial outer valence, so we will show that. And go back to that, you see that is 1-to-1 ratio. Lithium lost 1 electron, and fluorine gain 1 electron, so you don't need like 2 fluorine, or neither you don't need like 2 lithium, so just 1-to-1. But sometimes those need like those ratio you decide, right? Let's say you have that oxygen atom. Oxygen atom has 6 valence. So oxygen atom want to like neon, noble gas. So if you take oxygen with lithium, and each one lithium can only give you 1 electron. That is okay with lithium. Lithium now become like helium-like and become stable, right? But oxygen is still not stable because oxygen right now still has 7 valence. So therefore, you need another lithium. If you have 2 lithium, and each one lithium give 1 electron, and then both lithium become like lithium 1 plus, then that 2 electrons come from both lithium together. You give that all to like 1 oxygen, that becomes 8. Right? And you will see like a 2 plus and attracted to 2 negative. And by the way, so therefore the ratio between Li and oxygen is Li2 and O. So you can use this very basic process to see how many electrons the metal can give you, how many electrons the non-metal can accept, and try to make that number even, matching. Okay? So the total number that the metal atom give out so equals the total number the non-metal accept. Okay? Obviously, as what we saw in the last example between lithium and oxygen, in this example we have a calcium and chlorine. So each calcium atom will give 2 electrons very easily. But if you take the calcium with the chlorine, then chlorine, each one chlorine only need 1 electron to become stable. So therefore, you want to make a stable compound between calcium and chlorine, what you have to do, you have to take 1 calcium, for each 1 calcium atom, you need 2 chlorine atoms. Because each 1 calcium atom can give out 2 electrons. And one of the 2 electrons will go to 1 Cl atom, and the other electron will go to the other Cl atom. So when that happens, both Cl become Cl1 negative, then that 1 and only 1 calcium become 2 plus, and then all the 3 atoms is stable. So when they are stable, then you talk about those bonding attractions. So therefore, we see the ratio between calcium and chlorine is calcium 1 and Cl2. Right, so that will be our first CRE. Do we have the spectrum for this Chapter-9?
No.
So,
Do we go on
we will start a new
1.7?
one. Huh?
We have to start anew?
Yeah, well, I think we have something new. We have enough from the Chapter-7. We don't have enough. How many we have left?
Maybe there will be enough, because we've got 19 questions.
19 questions?
19.
And then probably not easy to. Let's start like on a new one. So write your name and then write Chapter-9. So we are going to use this for Chapter, also Chapter-9. So what's the answer? I think in this chapter you want to practice matching the electron transfer.
Is it D?
It's D. And so we learned that in chapter like in chapter 2 or chapter 3, right? So we know that Mg produces 2 plus. That means Mg will give out 2 electrons. Each Mg give out 2 electrons, and N will produce 3 negative. Right, so you want to matching the electron transfers, so we need 3 Mg. That will give us total 6 electrons. Then we will need 2 nitrogen atoms that will accepting the 6 electrons. Because each nitrogen atom can accept 3 electrons. Right, so now this will be the main focus of this chapter, which is about Lewis' theory of covalent bonding. So Lewis' theory implies that another way for those atoms achieve the so-called octet is by sharing electron. Okay, so again, whether they transfer the electron or they share the electron to achieve the octet, and that octet has that 3 deception. So some of those, between some of those atoms, when they like share the electrons, and those, so one atom will have like a less than octet, some of those atoms have more than octet, than some of those odd numbers. So then the sharing of valence electron is so-called the covalent bonding. And so when you have those atoms together, they cannot totally lose the electron, they cannot grab the electron away. You share that, and you get the use the Lewis theory and get where they share, how much they share, where are other electrons. You not only you share those electrons to make up the total octet, and some of those electrons is not really shared according to this theory. This theory kind of localized this. So this Lewis theory, they either those electrons belong to the atom or between two atoms, but in reality, those electrons actually floating over all the atoms, but most of the time they probably were spanning in between two atoms. So then you have, according to this theory, you have those terminologies. You have the so-called bonding and lone pairs of electrons. So that we have to memorize that. What is bonding pair and what is lone pairs? Right. For this given Lewis dot structure, there are many pairs of dots. Okay. So some of those pairs here we will see the bonding pair. And some of the pairs here, we call them non-bonding pairs or lone pairs. It's very straightforward. Right? So one pair here, two pair here. For that oxygen on that left side, there are two lone pairs. Now for that oxygen, you have two bonding pairs. One pair here, one pair here. That two pair is the bonding pair. For this sulfur in the middle, there's one lone pair. Lone pair. That lone pair, that means according to this theory, it just only belong to that atom. Right. Now for this sulfur, you have a three bonding pair. Yes. One bonding pair here, another bonding pair here, another bonding pair here. Now this triple bond, double bond, referring to if you share like two pair between the two same atoms, then you have a double bond. So even though this sulfur altogether has three bonding pair, but what we can see for this sulfur is one single bond here, so this is a single bond, but that's one pair. Then we have two pair here, is a double bond. So altogether is a three bond, but three bond, if you separate a double or a single, you don't call that a triple. Triple means you have all the three pair between two atoms. Okay? Similarly for double. Okay? Alright, so that is really very straightforward. So then to get that last picture, to get this picture like this, oxygen, sulfur, oxygen has those kind of two pair here, one pair here, three pair here, lone pairs. To get those kind of sort of Lewis dot structure, and the Lewis structure of molecules, you pretty much just use that few steps. That few steps, the important word is the so-called collecting all those valence electrons from all the atoms, then you distribute. So you at some point you forget about how many electrons that come from what atom. You just think all of them together. Okay? You produce a molecular, and you just collecting all those electrons, all those valence. See how many total you get. Okay? You might get 24. You might get 11. And you might get 32. So whatever you get those total number of valence, then you distribute. So that's a key word. Right? Now distribute, now you have to see those details. So where you distribute. Right? And you distribute, pretty much distribute them into the bonding pair and the non-bonding pair. Right? Now where you put the bonding pair, how much you put, right? And where you put those non-bonding pair, how much you put. Those are the details. Once you have the structure, once you have the Lewis dot structure, that is very powerful. It's very simple, and you can use it for many of your chemistry class. It can help us predicting the shape, predicting like those reaction mechanisms. Why is that there's a double bond there? Why the double bond you can add in water, produce alcohol, and so on. It's very, very important. Right, so here pretty much just repeating what we see those exceptions on one slide. Right? And that slide, you talk about the exception. When we talk about that, you talk about the ionic bond. Okay? Ionic bond, covalent bond, we have the similar like the basic line, which means we want to be stable. When is stable, stable is noble gas. Okay? So therefore, whether you lost electron or gain electron completely becomes stable, or you share electron becomes stable, same guiding line. So therefore, we have the same interception. What are the exceptions? Three major types. Okay? So those few less than our type, lithium, hydrogen, Be, boron B, even aluminum Al. I might give you some of those examples problem too. That's also exception. If you give Al like a 4 chemical bond, 4 single bond, which means you have 4 pair of electrons, that will make Al has orbital. When Al becomes not stable anymore. It's kind of those exceptions. So if Al and boron B and Be, if they don't have orbital, they become stable. If they don't have A, they become stable. You give them an A, the opposite, they become not stable. And you can explore those possibilities. If someone needs orbital, they don't have orbitals, that means they are become very active. And you can try to inventing some of those methods and try to inventing some of those chemicals. Put an atom in there that don't have orbital. See if that becomes stable or become active. Right. And so that other exception has more than orbitals. And what atom can have more than orbitals? More than orbitals, that means you might have 10 or 12. To have so much electron nearby you, you have to be strong enough and to be able to attract to make all the electrons nearby you stable. So therefore, you need a relatively larger nuclei, which means you need more proton in your nuclei. So what are those nuclei? They are in the period 3, or like beyond. Okay? A typical example, you will start with phosphorus P, sulfur S, right? And the odd numbers. So some of those atoms or some of those molecules, you put them together, you get an odd number. You might get like 17, and you might get 11. So then you share it with a double bond, you share it with a triple bond. Then one of the atoms will have a 7, or maybe have a 9. But some of the atoms will have an odd number. So those are the 3 exceptions. Right? So these are the few steps you follow to get the loose data structure as you see on my slide for that sulfur dioxide. Right? So after a few practice, those steps, I think you should be able to memorize just as you memorize the rule to calculate the oxidation state, some other rules. Right? So you want to distribute all those valence electrons, you need to have a place to distribute. Therefore, you first write the skeletal structure, which pretty much the layout of those atoms. What atom in the middle? What atom is a terminal? So altogether, you have a kind of a preliminary layout, right? So when you think about that, you just think about you have a 2D. You don't have to think about three-dimensional geometry at this point. So usually you will see there's some hint. If it is really difficult for us to find out what is in the middle, what is in the so-called terminal, the problem will give you, tell you who is the center. So you think about who is central. And so there's a few hints. The H can never be center. And then similarly, unless you have two atoms, you can see each one of them is center. And then similarly, those atoms in group 7A, fluorine, chlorine, and bromine. So those few atoms, most stable, they produce only one chemical bond. If you put them in the center, that means either at least left side, right side. That make it become center. If you only have one left side, you can call that center, but not really center, right? So usually you have a center. Some of those molecules maybe have two centers, so we'll say that those become like more and more. So once you have that structure, so remember you never put the H and those group 7, there is F, C, L, B, R in the center. Commonly, but you will see protein become center in the transition state. Because you see in the chemical reaction, maybe two molecules bonding together, then that kind of not a molecule, not your final product yet, but it goes through that step. You might have the, in the middle, that's not really stable molecule, not a really stable something. So usually, the stable one, you will not put an H in the middle. You will not put those 7A in the middle. Right? So then, if you have those oxy acid, you know what we studied in chapter 4, oxy acid, which means it's acid and has oxygen in it, and according to one definition, acid has H. So then, where you put the H? You can put the H, for example, the carbonic acid. So you have H there. You think about putting that H will bond into the center. You see the center is carbon. Right? But you also remember for those oxy acids, so the H is not really bound into those center. So those kind of you have more than one center. Right? Okay, so what I mean like this. So if you have those oxy acid, and let me see that what I talk about in the carbonic acid, we have H2CO3, right?
So it's going to be in the middle.
No, the C is the middle, right? And then you have those oxygen. Okay? So then those oxygen, initially you see that are not in the middle, so you see that is a kind of a terminal, right? And then according to this, so this H is bonding to that. So H bonding to that. That makes the O kind of also the middle. So you have some of the molecules that have more than one atom that's also middle. So then all those connections like this. So this is our
Double bond for one of them.
yeah. So then later on we have to worry about making sure. So we have to be careful, making sure every atom has the so-called octet. If you don't have enough electrons to make them has octet, you calculate how many electrons you have, like in this second step. Right? You're counting. So each H has one valence, so 2H gives you 2. Each carbon has 4. Each oxygen has 6, so 18, 22, 24. So you have 24 valence electrons available. Okay? So that once you finish those distribution, so what I did here is just make those lines here. These are the priority. Okay? So that's the detail. When you distribute, where you put the electron first? Obviously, it makes sense. You want to make a molecular. You need to put some electron in between those atoms, even though that's not really a very powerful theory, because you kind of see our name is these two electrons right here, but in reality, that's not always true. Right? So at least get some idea. You want to distribute. As the priority of distribute is to put one pair first, and don't worry about double or triple. Just put one pair, because each dash is a pair. Right? And then you examine like going on, and so yeah, get one please. Right. All right. So now let's review the first two steps. Right. So you lay out them like this. Right? So if I have another example, right? If I want to draw the structure for CO2, I will see who is in the center. And according to this, okay, you don't have H, so don't worry about H. And you have two type of element, carbon O. Yeah, one, very good, right? So one, like hint tell you, so those kind of called binary, remember what we studied in chapter 3, right? Binary molecular compound has only two elements, right? And you will put that least electronegative atom as center. So even though we did not study that yet, right? So this least electronegative. Right? Electronegativity is not a pattern, and we will study later on in this chapter. Well, pretty much is going from left to the right in the same period increases. Right? Going from bottom to the top increases. Right? So you compare carbon and O, they are on the same period. Carbon on the left, oxygen on the right. Okay? So carbon is less electronegative. This word represents the ability or the strength of those atoms attracting electron in the chemical bond. So that tells us if you have that electrons between carbon and O, okay, then those electrons will be more likely nearby oxygen, because oxygen has that electronegativity larger. If the difference is large enough, that will become ion. So the oxygen becomes ion, then other one becomes anion, other one becomes cation. Right. So it makes sense. You first of all just put those less electronegative atom in the middle, because later on you will see the procedure. Right? So you will put those electrons as lone pair on those terminal atoms, which is more electronegative. And that will give them a chance. You put them those lone pair on them, that totally belong to that. Then we will learn, like the last few sessions, a way to calculate the so-called formal charge. Okay? Then we'll see the formal charge will tell us, it's a kind of approximation, how many electrons those atoms have in the Lewis structure compared with how much they bring in. That will give you a kind of a sense. Do they gain little electron in the molecular, or do they lose electron in the molecular? And then you will get some idea in your molecular which part is relatively negative, which part is relatively positive. And this is the important point to study organic chemistry. Organic chemistry is to find out which part of your molecular has positive part and which part of the molecular has negative part. And then most of the chemical reactions, there are some of those free radical reactions like this, but most of the chemical reaction of organic chemistry is the negative combined with positive.
I mean, if you had enough pressure and heat, can't you just bond just about anything?
Yeah, you put not a bond, you will produce either solid, you have enough pressure, if you cool enough, your temperature low enough, your helium will become a helium solid, become like a very good crystal, but you still don't think that's a chemical bond. And so some of those material you can, yeah, when you have enough pressure, like some of those stars, when they die, they become a neutron star. which means everything collapses, nothing exists, only neutron exists. The proton in the nuclear combine with electron, proton positive, electron negative become neutron. Everything becomes neutron. That's called a neutron star. There's a neutron star outside in the universe.
Sounds very deep.
Oh, there's next week. Next week there's a professor of physics. He or she teach astronomy. She's gonna, I think Tuesday. Did everyone get the information? And he's gonna holding like one show or one talk and talk about how the scientists find out what element is in the universe. I think that's kind of interesting. How you find out. You find out, for example, there's a lot of hydrocarbon in the atmosphere of Jupiter, in the satellite of Neptune.
Can you figure out by like the temperature of like, the color it emits?
Yeah, they pretty much measure like what we did in the lab. They use those spectroscopies
Yeah.
and measure the wavelengths. I think that's kind of give them some idea. I think that's probably accurate. Because at least they launching some of those spacecraft onto the Mars, and then they can dig out some of those and bring back and confirm that. Yeah, Mars has an atmosphere, but somehow due to the solar wind, it's find out where the atmosphere air in Mars goes, because there's a solar wind. Solar wind are those ions, those radiations. Toward that will not hamper our planet, right? Then there's a. So once you have the counting the total number of electrons, you distribute. You want to begin with sort of the priorities. That means you want to, like what I did for this example, you put like two pair of, like two electrons first between two atoms. For carbon, so as you know, like as Mike said, the carbon in the middle, so you have oxygen and oxygen like that. Right? And so then you also like put one pair of electrons between each atom first. Very, very important at the beginning. I know like from the previous class, a lot of people try to rush into, I remember somewhere I saw this double bond from my previous class, I remember the double bond between the carbon and O, but you follow the procedure, you will get less mistake. You first just put one pair first between all those center and terminal. And then, once you have all those connections, that kind of give you a glue. So you have those structure ready, and then you just try to finish the so-called orbital. We call it, in both covalent bonding theory and ionic bonding theory, the basic line is all the atoms try to have the so-called orbital. Not really everyone orbital, you see those exceptions. You never give H orbital. H only have one proton. You give H like 3 electrons, it cannot hold the 3 electrons. So what do you do? So once you have the one pair between the center and the terminal, then you just proceed to the lone pair on the terminal atom. If you have like more than one center, you leave that the least electronegative atom, the final center. So here you have carbon in the center, you have oxygen in the center, oxygen in the center. So usually the problem gives you probably a right problem, which means it's stable. Right? You will have enough electron to make this become a duet, that's already a duet. To make this O has octet, so right now has quadruple, so has 4, so you need two more pairs. That one also needs 2 more pairs. That one needs 3 more pairs. Usually the problem will be enough. So you will have enough electron, otherwise your power you're not stable. Right? So you will have enough electron to finish all those atoms has the so-called orbital except the last one. Okay? So this is a procedure. So then you can take a time out. Okay? Then you recounting. So then you will see how many you have in step 2. And how many you have if this one already finished. This one has, if I do something like this, right? So if I want to complete, so I will put 2 pair here, 2 pair here, and 3 pair here. And that give all those terminal and has orbital and also this kind of middle orbital. Right? So then you take a time out, take a break. Right? And in the break you will see how many you get in step 2. And how many you get right now on this. How many shall we get on step 2 for this molecule again? What we said? 3, 6, 18, right? And then 20, 24. Right? So for this carbonic acid, right, we have a 24. So this step, right? So this step, we have a 24. You have 24. You can see this is available. You cannot have more than 24 on your final structure. You cannot have less than 24 on your final structure. Right? Yeah. So very, very important. So usually the exam question or the quiz question will give you some of the structure has more or less. And then a few of them is right. Right? So one important index you want to check is in the field choice, do you have the right number of electrons? And we talk about those valence. Right? So you distribute first between those atoms. Then you finish the orbitals for the terminal. Right? So now we did not check this carbon yet. We already checked this H has duet, that's perfect. Right? This H has 2 electrons, that means these 2 electrons. But in this step, in this chapter sometimes it may be confusing because you have a different way to think about the electron. So when you draw the loose structure, this dash means 2 electrons. And when you count in the so-called orbital, you will see both of these 2 electrons belongs to this H. So this is one way. Okay? Now later on you have another way. Okay? Now vice versa. If you see these 2 electrons, when you count in the orbital for this oxygen, then both of these also belong to this O. That makes sense. That means by share. Right? Now that's no doubt. That 2 electron, you could write that explicitly. So that's, you see that only on this O. So that's on this O, this on this O. And in this section, when you count in the orbitals, so these 2 also belong to this O. Right? So that's why we get orbital for this O. Get that now? Right? Similar for this oxygen orbital, 4 pair. Right? This oxygen get the orbital by have 1, 2, 3, that long pair, plus 1 bonding pair. Right? So now all those atoms has the so-called orbitals. We see carbon, we did not check that yet. Right? So usually, that's why I say you don't rush to double bond, triple bond. Take your time out, okay? See how many you have available and how many you have already used. 24 available. Okay? How many already used on this structure? 24. Okay? You do a very quick calculation, you can just write out. So 24 minus 24 equals to 0. So you don't have any electron left over. Right? If you have left over, you will go to that step 4. And if left over, you will put that on the center. You don't have left over, so therefore you cannot do anything. right? You put on the center atom, if you have leftover, even though you do that, you still have to check, make sure if you put that leftover on this may not have overtap. Right? Remember our basic line, our bottom line is everyone has overtap, not really overtap, right? Have something like overtap. Okay? So therefore, always keep in mind, try to give them at least that overtap. But sometimes you will learn more and more. We can have more than overtap. We can no matter what we do, we cannot have overtap because our number. Then we sum those atoms, we try to give them less than overtap. All right. So you don't have leftover. If you have leftover, put on carbon, right? Now that is what you see. You will have to use double bond, right? See, if any atom lacks an overtap, that means in this step, overtap okay, but carbon has only 3 pairs of bonding, right? So carbon don't have overtap, right? So what you can do, you can take like you kind of like doing those back and forth. So carbon and O and H and O and H and so not O here. So initially I put something like that, right? Yeah. So right now this carbon has only 6. One way to make this carbon has 8 is to move like this one pair of electron, redistribute. And now you will have that. Right? So carbon here, and you still have 24 electrons, okay? So make sure you don't have more than 24, and you don't have less than 24. And make sure try to have everyone has overtap, not a little overtap. Right, so this is theory. And later on we will talk about some of those extensions. So how can we make the model or theory better? Right, so now let's do another example. Okay. You want to draw the loose structure of this guy. Okay. The first step, you want to have the layout or the skeletal structure. Okay. So now let's decide what atom should be our center, or what atom should be our center. The center should be what? The big center should be N. Then all sides should be what?
Oh.
Oxygen, oxygen, and oxygen. Now what about the H? What atom the H is going to attach to? Right?
Oh, and
So because oxygen acid, not that,
oh, it's that.
not that. You don't want, that means,
Oh, just touched.
you don't remember that, right? So what you do, you will see that H is bound into 1 with O. Now which one you going to bond into that doesn't matter. Right?
Which one you bonded to, doesn't it change like the shape of it?
Yeah.
What if the other two like?
So that will change that little bit, but
Would it be like down or wouldn't it be like?
yeah.
Well,
So
it's 3-dimensional, so it doesn't really matter.
yeah, 3-dimensional, whether the bond angle is perfect 120.
Like we're gonna learn later on, there's degrees to it too, like 180,
yeah.
160, all
The
that.
bond angles.
The bond angles, right? The bond angles, yeah. And so that's very important, very basic. Now, what you do is you get this idea, okay? And if you want, you can draw like one line, which means one bonding pair between each atoms. You can draw something like that. Even though this is kind of jumping according to this procedure, but this just help you to know like what is the connection, what atom in the center. Okay? But otherwise, you probably get a little confused. All right. So then next step, you want to do what? Yeah, count out. So adding together what is our total number of electrons. That's very straightforward because we, as I said, most of the time we talk about those group A elements, right? If you have those ion, you have to think about adding one for each one negative charge, and subtracting one for each positive charge. And this is not ion, so therefore we don't have to worry about that, right? But what do you think? So this H gives you how many? Give you 1, right? And N gives you how many? 5. 3 O give you 3 times what? Right, so altogether we have what? 24 valence. Right? 24 valence. Right? So then you go to the next step. You see, I want to distribute. I want to distribute this 24 electron. Right? Right. So now let's go on to the next slide. So that's what we get. In the distribution process, make sure you just use one pair first. Okay? Between the atom first. Right, now what do we do next? We already did the first step of 3. Step 3. The first step is distribute between the atoms. Right? Now what is the next step in this step 3?
Put the valence electron.
Put the valence electron on the terminal, or maybe those not the center atom. Maybe them has the so-called what? Orbital. Right? Right. So now let's see which one will be our really the last center. Really the last center. So this will be my last center. Right? Why that? Because I will say like compare N and O is more electronegative. Okay? So even though that O is also center, but that is kind of outside terminal. Right? So you will leave this N, the last one, to consider. Okay? Before you consider this N, take the time out. Okay? So let's see, do we need to put any more electron on the H? Very good. So this H already have a duet. What about this oxygen? How many? 3 more pairs, right? Right. So 3 more pairs, and so I'm going to change the color for the long pairs. So I will put 1 pair, 2 pairs, 3 pairs. That will make this oxygen altogether 3 pairs plus 1 pair, 4 pairs. That's perfect for oxygen. Right, now what about this oxygen? Similar, right? So that also need 3 pairs. And 1, 2, 3. Very good. Now you don't take time out yet. Because you want to leave only 1 atom you don't check yet. Okay? So you keep going until the last one. Okay? Usually you don't worry about if you don't have enough electron, if the problem gives you right again, you will have enough electron to finish the orbital for all the atoms. Right? Right? Again, do we need to do anything for the H? So that already have orbital duet. What about this O? How many electrons right now, in terms of the loose structure, how many this O right now have? 4. So you need 4 more, right? So we need 4 more. 1 here, 1 here. Very, very easy. Very, very important. Okay? Don't think about something easy, you just jump in the step. You see, I know like this double bond, you just jump in the double bond. So don't jump in the double bond yet. Okay? And the double bond, you can even make more double bond later on, use the forward charge. Okay? So for this section, just follow this few steps. Okay? So then we will take the time out, because we did not check this N yet. Right? So now let's see how many electrons already used, how many electrons that are available. We said from the step 2. Step 2 tell you we have 24 valence electron available, right? Now, how many electrons that already used in this structure? 24. Do you agree? Right. So therefore, you have 24 minus 24 have a 0 left over. If you have a left over, what do you do? In this example, we don't have a left over, we have a 0 left over. If you have a left over, where are you going to put a left over? On the center, on the last center. Okay? Now, in this one, we don't have. Now, you still have to check whether you have or not. You still have to check the last atom. Do that atom need an octet? It doesn't need an octet. It's not a DE, not a boron, not AM. So need an octet. If it needs an octet, somehow you have to make it have octet. And what we did here. Right? What we did here. Right? What do you think? How can we make this N has octet? Double bond between what and what? The better is between this N, between this O and this N. Right? Right? So you can see what we can do. You don't like adding like this. You don't like adding 2 electrons on that. Okay? You redistribute. So what you do, you take these 2 away. See what I did? Okay? So I take that 2 away, and I will put it here. If I put it there, it's the same as, if I put it here, it's the same as a dash, a chemical bond. And that is the importance of sharing. If you put that, these 2 that still share between this O, between this N, that means it still belongs to that O, but at the same time it also belongs to the N. And that? Now it's kind of perfect, right? So everyone is happy. N has 8, that O has 8, and this one also has 8, that one also has 8. But then according to the theory, one theory will say, you probably can even do better. Right? And you will see, like, you calculate the so-called formal charge. So what the better one is, everyone don't have any formal charge. That means what they bring in is kind of what, Republican or Democrat. What you bring in is what you have. But in reality, it's not that perfect either. So no theory is perfect. Okay? I think that this is the final result. Even though if you do the formal charge, you will see in like 1 second, you will see this oxygen has -1, this nitrogen has a +1. So probably that's not the best loose structure. I think according to some of those theory, some of those experiments they measure, then that's it. You don't want to like take another pair here, and you will produce like 5 chemical bonds for this N, and then that's according to that theory. But I'm going to tell you that theory. So that theory works for some of the molecular, but doesn't work for some other molecules. Right. So then, this I don't know what is the best way to organize those topics of this chapter. When we talk about this, naturally is kind of you are thinking about another concept called the resonance. Right? What the resonance means. Now for this problem, we take that electron away from that O, because initially that O has 3 lone pairs, and then we share that 1 pair, make that O still has octet, make this N has octet. What do you think? What in your mind when we do that? There's another O, right? What do you think? Maybe give that back, right? Yeah, so that's a similar idea. If instead of like what we did here, right? So you need to have A and O, 1, 2, 3 here, and O, 1, 2, 3 here, and another O and H. So what we did is move that. Right? And that becomes A, double bond O, and 2 pair left over. This O, we did not use it. You can try that either, but that will make that O has a 3 chemical bonds. 3 chemical bond for O is not very good. And you can, so that's what we did. So we see this is our, this is our step 1. And from our step 1, we produce this. Now starting from that molecular, if I do that, I call that a different step, step 2. And we don't do like step 1 and step 2 together. So we either do step 1 or we do step 2. Right? And then we'll have O, H, we still have this. If we don't do that, so that still has 3 pair. Now this have that. And this we call our step 2. The second approach. Right? So sometimes I was thinking about introduce that concept called the resonance when we talk about that. I think that will come up pretty soon. Right? That's natural. Because you initially have this kind of structure, and this has a 3 lone pair. That also has a 3 lone pair. What we did here is take that lone pair from that O, and if I don't draw those guys, this O and that O obviously is the same, equivalent. It looks like they're the same, right? So you can either take that from that, produce this, or you keep that and take that from this O, produce this. So these two structures, right? So these two structures, we call them resonance.
Does every compound have more than one little structure?
Most of them has more than one, but the problem is which one really dominates. So in reality, which structure you're going to use to representing the true picture. So for those kind of programs, this one probably 49%, 49%. That one still possible. That one maybe 0.5%. But some other still possible. So so you explore some of those. They exist as a majority or they exist as a minority. But don't think the minority is not important. The minority, if we show some of those characteristics, and then those chemists will capture those little bit of those extraordinary, the minorities. We can use that to design some of those chemical reactions. So those things about they all exist in the pot. Chemistry is about cooking pot. So you have all those exist in the pot. If you put some chemical in it and take some of those away, then all those will shift into that direction. So even though those exist not too much, but you take them away, then you will produce more of that. And finally all of them become that, and all of them will become chemical reactions. But in usual condition, let's see, if you have only this molecule by themselves, nitric acid, put in a beaker, and then most of them probably exist, either that. And then, yeah, so then,
How do you decide which new structure is like most accurate?
yeah, that's,
Based on like bond strength?
well, before I say that, I think one point I for image I said, this is 49%, that's 49%. But either this is 49% or that is 49%, not really, well, it's difficult to say, not really representing the true picture, but it shows some characteristic. But we can,
What conditions would that 1% one be?
1% wine.
That one on the top.
Yeah, I don't know how to use that one, but I know there's one reaction, they use this one. But I know some of those chemical reactions that can use those very, very less percentage of resonance structures. So you will see those in the organic chemistry too, the so-called carbonyl compound. For this one, I remember there's one chemical reaction use this, but that doesn't make sense because this is majority anyway. You produce the so-called TNT, and you start with like the, that one called toluene, which is kind of poisonous carcinogen, but they can use that and put that together with nitric acid, sulfuric acid, and produce TNT. So that it uses this. There are some of those examples to use that, but we don't have to worry about that. Anyhow, so then the other question is which one is better, right? Which one is better? There's one theory called the former charge. You will see in my section. But that former charge, as I see it, works pretty good for most of the problem. Well, not work for some problems. Yeah, because you use former charge, you are predicting, for example, ozone. Or the sulfur dioxide. So probably the best structure for ozone is that ozone has like O and O and O, right? And you probably will get something like that. That means you will have a double bond between all those atoms. I think it is permanently they find out that the bond between those not really a double bond. So, yeah, the former charge works pretty good for most of the atoms. That is like one extension to the so-called Lewis structure. Lewis structure has two extensions. One extension is about this resonance. And the other one is use former charge and make more bond. So you probably will see some of those, if you use former charge, it works pretty good, That means you will have the, for example, sulfur, not only have the octet in like a sulfuric acid, it has like two of those double bond, and then make it become like six chemical bond. 6 chemical bond, then that make it former charge become 0. That works pretty good. Yeah, I think that this is the kind of fundamental theory important. Probably, if you have time, you can write some articles on the chemical education. But if you want to do a research on some of those really journal of chemical physics as a journal of chemistry, those guys, nobody talk about those. But it's very important, like in terms of those fundamental educations. Right. So what you do, you can take the electron away, and I don't know what time it is. But anyhow, this is one structure what we showed here, right? And you can do the opposite. You kill this two here, and you take that two away. And sometimes you can do two at the same time, depending on the molecule. If it's sulfur in the middle. For this example, as I said, don't do two at the same time. I think that's for this problem. For some other problem, you probably can do that two at the same time. I cannot tell like beforehand. All right. So another example is CO2. We can remove that. So you have that CO2, and you already see that structure, the carbon in the middle and oxygen on the two sides. Now we know. To make this clear, so I jump one step again, so I will just make one dash. Right? I usually don't do that, just keep like carbon in the middle, and two oxygen in the terminal. So what you do next is counting the valence. If you have iron, adding subtracting. Right? Now this is not iron. So what you do, you will have one carbon, one C give you a 4, right? and you have 2 O's that will give you how much? You all together 12, right? So you adding together gives us 16. Right? Now you just use this keyword, distribute. Right? So I write that at the beginning, that means it's very important. So you first don't do anything else. Put 1 pair between the atoms. And usually you don't do something like that. You don't put another pair between these 2. you can have some of those like the triatom, like triangular structures, but so here we just see this. So if we don't consider those cyclic moleculars, so we just very straightforward. Right. So now what you do, you just once you have the bonding, you just what do we do next? What do we do next? We make this O. I see if this O needs overtime. If you need, make overtime. And similar for the other O. So what do you do? And you will put 1 pair. Is that enough? No. So you need like 3 pairs, right? So you usually will have enough electrons, right? And to finish those terminal atoms, right? Only have 3 atoms. So 2 of those atoms are the terminal, right? And that already finished all the test. Usually you will take a break, okay? Before the last atom has all the test. Okay? Very important, okay? So now you take a break because you already have all the atoms except the carbon. Okay? Very easy counting, right? Here is what?
Double bonded.
Here is what? On that side is what? All it has 8. On this side, 8. So 8, how many you already used in this cycle? 16. Okay, now you have 16 and 1 also 16. 0 left over. If you have a left over, you put the left over on where? On the center, on the last one. Okay? Now we don't have a left over. Right? So either way, if you have a left over put on the carbon, you still have to check. I will see something example pretty soon. Even though you have a left over, you put on the carbon, you put on the center still don't have overtake. If that is for boron, beryllium is okay, right? And if not the exception for some of those not atoms, you need overtake. So what do? Now you think about Mike use what?
Double bond.
Double bond, right? You can use double bond. Right?
Put on both of them. Since
You can. That's one of the best. That will be the best. You can take the double bond from both oxygen, and you will produce 2 double bond. You will produce 2 double bond. That's the best, right?
Because carbon likes to keep away.
Yeah. Right. So what we do, we'll take 1 pair from that O, and another pair from that O, like that. Now if you do that, you still have this number of electrons here right. So keep that in mind. Okay? So what you do, you don't want to lose some electron, or you don't want to put some extra electron on it. Okay? If you calculate you have 16, so your answer you keep in mind should have 16. So what else you can do to make everyone has all the time? We're starting from this carbon and this O, have a 3 pair, and we have this O, have 3 pair. What we did is take 1 here, okay, and take 1 here. If you do 2 steps, you will see after you do 1 pair, make that the carbon has 6. That's not enough. You do another time, make that has 8. That becomes this, right? Any other way you can make the carbon, make the oxygen, make everyone has an overtake.
You could put the dots on the C if you want.
You put the dot on the C.
Because you look for an alternative way, right?
Yeah, you can do that. So you can put that as a dot on the C.
Two dots, yeah.
Put dot on the C. And,
It'd be weird, but yeah.
So let's see that it works or not, right? What do you think? You think like this way?
Yeah, I mean, that'd be weird, but yeah.
Yeah, it's not weird. It's not weird, but that means you kind of,
It makes the bond really.
I agree with you, kind of weird.
It makes the bond really weak, really.
There's also, what the problem is, this, no, this carbon, okay, has overhead, right? Now this one, what?
Has like six.
They don't have 6, and that one has on it.
6.
So that's, probably again, those will be minorities, but not that important. What else you can do?
They're very rare, yeah.
It's really weird, yeah. What else can I do? So I think that's, we probably will not consider that as a matter of contributor, okay? So sort of the contributor. Because it's obviously, the best contributor is, you at least you have that overhead rule, then you have the formal charge. So everyone has a super overhead, so that's better. Okay? And this one clearly that don't have overhead, so that's not the best. What else we can do? So this one is important. We can see it's important. The so-called measure. Those probably very, very minor. Okay? When you don't have overhead, it's really, really minor, very, very minor. So think about what you can do. There's some other way to make the carbon has overhead, and also all the oxygen has overhead. What do you do? What do you think, Jack and John, Jill, what do you think you can? There's some other way. Mike can think that way. I think that way is very, very minor, because that will give that the carbon has 8, but 2O don't have 8. What other way?
Could you connect the O's together?
Hmm?
Could you connect the O's together?
Connecting the O together, yeah.
Somehow?
Yeah, that's really, really not zero, because that's the angle strength too much. Right. So if you somehow make this carbon and this O and this O and connecting them together like that, and so this one need 4 more like that. It still has orbital, and then there's only 4 electrons. What else you can do?
Another one? I don't
Well, let's see, how many electrons here we have all together here? 1, 2, 3, 4, 5, 6, 7, 14. That maybe a little different. There's 14 electrons. That means you have
know.
2 electrons left over. You can put on that.
I mean, if you want to do negatives and positive,
You can take this away, and then you get that become double. That's perfect. That's everyone perfect, right? But this is really going to be minor. Because of so-called angular strength. See the angle here? What's the angle between these 2 bonds here? It's a triangle. And later on in the next chapter, so the angle here, approximately what is the angle here? How many degrees?
180,
Huh?
180, 120.
Okay, we have to review our geometry. Right? So it's about 60. 60, and then we later on will learn the bond angle. I think no bond angle that on carbon that has ideally is 60. Okay? I think the small one for the carbon is 109. I think that's 100, about 100. Right, you did not think very like, you are not thinking. So what we can do, we can like take one pair here, take another pair here. So we will have 3 bond here, and then we have this 1 bond here, right? So instead of like you have a double and double, you can have a single and a triple. Alright, so then we try to better again, you can use in my section the sort of the formal charge. That works for most of the problem. It works for this CO2. Alright, so you have this 2 possible resonance structures, or 2 important ones. Find out about for this section as in the root theory, so that's what we know. Alright, now you do a practice. So choose the best root structure
Is it B?
according to what we said, what we studied so far.
Is it B?
B, okay, I see 2B. What else? B, B. Okay, just B.
Yeah,
Just. So for those kind of programs, as I said, one important point you want to keep in mind is first check whether those number has, whether those structure has the right number of electrons or not. Usually, so some of the structure will not have the right number of electrons. And then you will see like the other typical mistake is what atom is the center. So as I said before, H cannot be in the center, Cl cannot be in the center, and so therefore that will get rid of that guy, that's Cl in the center, and then they get rid of that guy, so that's really gone, that's really gone. And so what is wrong with D and E?
there's not enough electrons and there's too many bonds.
So yeah, that's the D, so this, and then carbon, for E, there's, carbon cannot have, that, how many? 6 bond.
Why couldn't it be A? I'm sorry.
Hmm?
Why couldn't it be A?
Why cannot it be A? A, the problem is the Cl, okay? So those halogens, you probably use some of those become very, very active species. Usually the Cl will not have 2 chemical bonds.
And doesn't carbon always have 4 bonds?
Carbon always have a 4 bond that's stable, but in some of those intermediate, not stable final products, you might have those carbon cation, or maybe a carbon anion, which means you might have a 3 chemical bond, and then you will have you will see there's an empty p orbital. You might have a 3 chemical bond, then p orbital that has 2 electrons in it that become anion. Typically that's right. So carbon will have 4 chemical bonds that is stable. Maybe like what we said in this structure, maybe 2 double bond, maybe a single, maybe a triple. Right. So very good point. If you want to have those kind of molecular that become very, very active, that means for some of the chemical reactions, and you probably use sort of the Lewis acid, the FeCl3, so you have a Cl in it, and then you can make the Cl bonding to 2 of those atoms, then those Cl become very active. They are not very stable. So what we talk about here is those stable, or those sort of the important or the major contributions. You can use broad those small unstable ones.
I can't. People around me can, but I
Yeah.
can't.
So need more practice. So radial structure for N3. So I will show you this one. You will have some of those leftover, and then you will put the leftover on the center. Right? So now what is our center for this four atoms? Hey, and then this kind of very straightforward, very simple. You will just write them out like this. Okay? To emphasize this N in the center, you can just adding like one line, one dash. Right? So then we calculate how many electrons. So this guy gives you how many? 5. Right? And the 3 H together give you how many? Give you 3. So all together you have 8. Very straightforward. Okay? So once you have the number of electrons, you know we have 8. And then you know this N is the middle, and the H is terminal. The H has duet is okay. Okay? So H, so this need the duet. So don't give the H like 4 or 6 or so just that's perfect, right? And so that's finished, that finished, that finished.
Doesn't it need 2 double bonds?
That's it. We need to talk about one, right? So that finish our so-called
No, wait, it doesn't.
octet.
No, it just needs dots.
Duet for H equals octet, right? That makes sense? So therefore, so we have all the atoms have octet except what?
Yes.
Except 1. And that is the time to take a time out. Okay? Then you calculate how many use, how many left over. So in this number, how many are available?
2.
Yeah, so we have two available. So what you do, you will put these 2 available on the center. On the center. Okay? Later on, you will see some of those exceptions. Even though you have a 3 pair, 6 left over, you will put all the 3 pair on the center. If you have 2 pair, you put all the 2 pair on the center. Okay? If the problem gives you right, and you should have a stable molecule or ion. Right? So once you put those levels over, and then you still want to check. Okay? What is our center? Our center, there's only one center, is N. Do N need octet? And N need octet, right? Who don't need octet? Hydrogen, lithium, beryllium, boron, aluminum, so those kind of small atoms. So nitrogen need octet, right? Well, nitrogen has octet. So Mike, right now, does N have octet or not? How many electrons that's in the vicinity
It has octet.
octet? Yeah, 1 pair, 2 pairs, 3 pairs, 4 pairs. So if you have 4 pairs nearby, so in terms of the root structure, that means this N has octet. And then you don't want to make a double bond. Okay? You don't want to not N, double bond H, single bond H, like that. That is okay with the N, but little too much for the H. Right? So very, very simple. And this is why this series is very important. You see, that is a stable structure. That means you have that long pair that available. Long pair of electrons is very important in chemistry. If you have that negative charge on your one place in your molecule, the negative charge, it will attracting to the positive charge. So therefore, ammonia is our typical base. Okay? That means if you have some of those other molecular that has H that are available, for example, water, and this pair of electron is going to grab the H from water. Yeah, that's what you smell, what you see in the ammonia. You think that the lab, like for that water hardness, you use like the buffer, right? And ammonia buffer, that means you have that you have some of those ammonia and industry gas buffer into water, and then you will see that become beyond that. All right. It's very, very important. So very simple theory. So because we have this structure is stable and we have that non-bonding pair of electron there, that can take the H away. So if you have some H available, for example, those H in water, water is a very simple structure like this. So these two electrons is going to attack that H. And then that two electrons will bounce onto that O. So what you will produce is N, H, 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 and H. This become our ammonium ion. And what left over here, the water, this become hydroxide. And then we know hydroxide is base. Yeah, so those like those drug medicines, so somehow they design those drugs better, effective, make them become some kind of salt. So they will change those base, neutral base, maybe into ions or something, make them soluble. Right. So that's why we study those general chemistry. Okay, so this molecule is sort of the molecule you usually will smell in some of those hospitals. If you work in some of those biological labs, the sort of formaldehyde. So used to preserve some of those examples.
Is it B?
The answer is B, very good. Okay, so you, as I said before, you should examine all the other answers, so you find out what is wrong with them, and that's is very good like, practice. Right, now let's see some of those ions, ammonium ions. It's very similar, just when you counting the number of electrons, it's a little tedious, right? So we have this ion, which is a potassium ion. According to the procedure here, you are subtracting 1 for each 1 plus. Right? For each 1 plus, you're subtracting 1 for the number of electrons. You again you have to first decide what is our center. What is our center? So these 4, 5 atoms, what is the center is N, right? Yeah, so center is N, then H, and H, H, and H. So again, you can jump in one step right now. You just make 1 dash, 1 dash. The purpose of doing that is to make it clear. You will see, really show you clearly what is the center, what is terminal. Otherwise, you have like a few atoms there, like you put in your mind, you know that, right? So now let's counting the number of electrons. 1N gives you how many?
5.
Over 5H gives you 5. 4H gives us how many?
4.
Gives us 4. Now what you have to do, don't forget those ions. You have a potassium ion, that means these 5 atoms together somehow lost electron. Right? Lost how many depends on how many plus. How many plus? 1 plus. Right? So therefore, lost 1 electron. Right? Subtracting 1. And again get 8. Right? Right? So you make the connection first between the N and H, N and H, and H. Right? So that's definitely that will be will be like the kind of one step jumping, but it will show you like what is the center, right? Usually the problem will be like you will have enough electron to do that, right? So once you have that, you know you have 80 electrons, then you just go to the next step, right? Distribute, that means you just make one dash, you have 4 dash, right? So then you will go to the next step, so then proceed to long pairs. If they need long pairs on the terminal atom. Now the terminal atom here is H. Do H need more long pairs? No. You just have like one bond for H, so that will be enough, right? Right? So therefore you finish all the orbitals for all the atoms, except the N, you did not check yet. Right? So then you just take a time out, right? See how many electrons available, how many you already use. How many available? Yeah. Initial 8. Now we have 8 there, right? So therefore zero left over. And you have left over, you put on the center. If you don't have left over, either way you have to check it to see if you have orbital, right? And this is very simple. This N right now has orbital. Yeah. You have a 4 chemical bond. A 4 chemical bond, each chemical bond gives you 2 electrons, so therefore you have orbital. Then you can see this is your result. That's your result. And for some of those programs, you can optimize, use those sort of formal charge, right? And those really depend on the experiment, because chemistry is empirical science. A lot of those theory depend on the experimental result. Now for the ion, not really the final result. You just put a bracket and put a plus. Not that important, but just formally. All right. So that is one more practice. And now you do a similar practice. Probably this one. You really don't have that much atom to see which atom is really the center. You can go by the priority. Okay? You can compare Cl with oxygen. The Cl is less electronegative. The Cl will be a center in terms of where you put the electron first. But finally, it probably doesn't matter. It becomes all the same. The result becomes the same.
Is it A?
A. I think right now D makes more sense. Probably that little different was to identify my. I think again you just use first check. Okay, very important. For all those given problems. Obviously, if I tell you to draw the structure, your second step will be counting the electrons, right? If I give you the structure, first check number of valence electrons, right? So this ion altogether has how many valence electrons? Very good, 14, right? Yeah, 14. Where the 14? The Cl give you how many? 7. And oxygen give you how many? 6. So this -1 then is what?
Add 1.
Adding 1. For negative charge, for each one negative, you're adding 1. So you're adding 1, so obviously you have 2 7. Right. So that's it. So then you have, I think for D you have 14 electrons, and more importantly, each atom has orbital. Right. you can try like something like this B, right? This B is also like 14 electrons, right? Now, what is wrong with this is later on you will see there's something wrong with the former charge. The former charge is very, very useful with very, very important like theory. It works very good for most of the problems. Now this concept, we already talked about that before, called resonance, right? Resonance structure, that means it's kind of one extension to the so-called Lewis theory. So we talk about two extensions. To make the Lewis theory getting better, we modify like two concepts. One is resonance, and the other one is the so-called formal charge. And these two go together. Okay? And you use the formal charge that will help you decide which resonance is better. It works for most problem. So why we have to use resonance? That is because Lewis theory is kind of, if you don't use resonance, it's kind of like they localize into like those between two atoms. As we said, for the reality of molecules, it's better think about those electrons as in those molecular orbitals. And obviously this theory has the limitation. And so then extension suggests that you probably can think about either you share the electron from the left side or share the electron from the right side. So then what is the best way is think about both atoms share the electrons, and so that kind of sort of delocalize the electrons. To delocalize the electrons is kind of release a lot of stress. Yeah, so usually if you have those electrons, ions reacting very, very quick. Right? So that means there's a lot of, the energy is very high. And if you can like spread out those charge, if you have a negative charge, right? And that become, make the result, the ion, all the molecule become much more stable. And so then you also want to keep in mind, well, the general chemical class or unit size, so what is the true picture for the molecular is sort of hybrid. Okay? So then, if you study the organic chemistry, they will consider those particular contributors. So use those particular contributors is much easier to understanding some of those reactions. Right? But for this class, you just keep this what this book said. This book, I think he emphasized a lot of those introductory chemistry, and some of those theory in like those this chapter 10. There's many exceptions to those what we talk about, those like the whisper theory. Use whisper theory predicting the geometry when you have 4 pair, the tetrahedra. When you have a 3 pair, it's trigonal planar. But then again, depend on what is nearby, what are the vicinity of the atoms. So you will see that will change a lot in real chemistry reactions. So study chemistry, you study some of the fundamental principles, right? Then you see you can also use some of those extreme or exceptions. Right, so we will take the hybrid thing about it as our representation. Well, depending on what you measure. If you measure like the spectroscopies, measure the NMR or the infrared, and then on the time scale of that, those will be enough to average out. So if you have ozone, you will not measure a double bond, single bond there. in the chemical reaction might happen very quickly. It will capture one of those possibilities. Right, so when we talk about those resonance, for example, ozone, is a very important molecule for our life because that will protecting our Earth from damage UV light and so right now we worry about the ozone depletion especially in the South Pole. So I think it kind of stabilized. In the 70s, people are really worried about. We measure like in the South Pole, there's ozone depletions, and ozone is a very interesting molecule. If you get into our layers we live in, which is below like that 10,000 meter, it become irritators, and you can damage your eye. It can damage those structures like plastic. So even this like beyond that the usual airplane flying layers. So there is a blocking is kind of is blocking like the UV light. You can see that again. This is the reality. So if you look at the literature, they will tell you the bond between O and O is not singular. A singular that means one solid dash. So one solid dash, then one solid line, then one dot. That dot representing maybe half bond, or maybe 1/4 bond, or maybe 1/3 bond, depending on the problem. But just make sure that it's not one solid bond. Right. So if you calculate the formal charge, the better way again is make a $2 bond. But I think there are some of those exceptions. So then you keep in mind this resonance. Resonance structures is not an isomer. Isomer that means is different compound. So this is for the same compound and two maybe equivalent, even not equivalent electronic structure. So what you will see in the resonance structure, the atoms connection is still the same. Only difference is where are the electrons. And so that gives us a sense the electron can really mobilize, can move. So this ion will like give us one example and see how many resonance structure you can draw, right? So again, you will first draw, use the Lewis structure. First draw the Lewis structure, and then you will make you will take the time break and calculate. Then you put it there. So then you will have a different way to put on there, right? Okay. So who is in the center? Okay, so make sure you identify that, right? So you have how many oxygen as terminal? 3 O, right? 1 O, 1 O, 1 O. Right? So what you do right now, you just use one dash. Even though we jump in again, right? Right. So then next we were counting the number of electrons. How many electrons that is available for this ion? Very good, very good. Yeah, so we have 3 times 6, that's 18, then plus 5, plus 1. Where did this last one come from? The negative ion. The negative ion. Where did the 4 come from? And where did the 5 come from? From nitrogen. Okay? This is 3 from this substitute 3, and this 6 from O. Very good. And so all together we have 24 electrons. So what we did before, we can even change the color of the pen. So I needed to put, so even though these are really going back and forth, I put on 3 pairs for each O, then I take it down to the back. Right? So that's okay, right? So you make sure you follow the steps. Okay? So I will complete the so-called order test for all the terminal. And I will always deal one atom. I maybe coincidentally also have order test, but I will not do that on purpose to see that make order test. So I will make sure I will check all the atoms except one. Right. So now we already have all the atoms have order test. There is only one that does not have order test. That is the center atom. So what do you do? Take a break, right? And see how many. Take a break. See how many available? How many already used? How many available? 24. Right? How many already used? 24. So therefore, we have a 0 left over. If you have a left over, you will put the left over where? On the last atom, which is the center. Right? So this one we don't have a left over. Right? So then either you have a left over or no left over. You don't forget, you still have to check if the center need an orbital. Right? Do we need an orbital for A? Right? So therefore you have to use what? Can you put like one pair here like that? That will make the A has an orbital. Right? Then make the A has an orbital. Now what's the problem with this structure? You have 26. We have 26. If you have 26, you know you need 24, right? So 26 is not not. And right. So we need to what we need to do is get rid of that too. Right. But what we do, we still want to like it. So what do we do? Take this one first, right? So we have an A, top one O, then this will have 2 pair left over. Then that 3 pair will not do anything. That 3 pair will not do anything. Do you agree? So then what is the other possibility? Just rotate. You can see like I will say, if you can do that from this one, why don't you do that from it? So you can just you will see like all those possibilities, and what you get might be equivalent. Yeah?
Oh no, I was gonna say, do we have enough time to do the lab?
Yeah, so this lab.
It's like homework, pretty much.
Yeah, that's pretty.
It's just homework.
Oh, is it?
Yeah.
Oh, okay.
Yeah. Right. So that's. Therefore, we have this. So we have these 3. We have this. So we started from. I think that's. We were starting from this. Starting from this one. From this. Which means we will have. Right. So we started from this. So each oxygen. And again, if you want to put this, you also put this in brackets, that's negative 1. Right? So each oxygen right now has orbital and 3 lone pair by themselves. The problem is N, and you can take which one you take, which pair, this 3 pair here, which pair you take down the matter, even though it looks like you take this pair, right? You can take this one, anyhow so you take one of these 3 pair from this O, you get that. Right? And then similarly, for this problem, all these 3, in terms of like the percentage-wise importance, yes, 3. So you can take one pair of electron from that and get this. And again, for this problem, you probably don't do like both of them at the same time. If you do that, it's okay if you have, that's according to, if you do like this, so if I delete one pair like this, right? And you can do that, and what the problem is, according to the former chart, maybe not working so good. Yeah, because I write pen. Right. So this program, the former chart now become. So if I do that, so this will become, this former chart becomes 0, this former chart becomes 0, this former chart becomes 0, and that former chart becomes -1, and that becomes -1, that's okay, because you cannot avoid everyone has no former chart, because this is -1 I. The problem is compare with this. You compare with this, okay? So what you get for this structure, so you get 0, you get a -1, you get a -1, you get a +1. So you get 2 -1, 1 +1, 1 0. Adding together again is -1. According to the former chart, which one is better? You will see the last former chart is better. So here you have 0, 0, 0, -1. Compare here with 0, -1, -1 +1. That's more from I did not see that. I think the less the better, but that's the theory. So we try to just when we study the former chart theory, we try to go with what the theory said, and I think that's about it. So that's how we study. Right, so finish that problem. So according to that, so according to this question, if I take this away, and so this last three structure is our residence structure. Then if I ask you how many resonance structure for this ion, okay? And you can create more, but those more not that important. Okay? So you will see that we only did 3. Okay? So I'll show you. You can put another one here. Okay? You have 2 double bond, 1 single bond, but that's not that important. Okay? I think
Would be the right way to be it, like, to draw that for one of those double lines to have, like, be dashed?
one of the double bond there. Yeah. So what you can draw, then you don't know, like, but you keep that in mind. You have 3. Okay? And you can draw all the 3 together, which are sort of the hybrid, or hybridize. That means you take all the 3 mix, and you will get a structure something like this: N, O, and O, and O, and you will use dash in all that. That's why the next question is about how many resonances you have. Yeah, so depend. I think that's a very interesting question. Yeah. So you see like 1 resonance for that benzene, right? Is like this. And obviously you can draw a double bond like this. Draw something like this. So you can see these 2 structures are basically only switch. The double bond here can become a single bond. Single bond here becomes double bond. And those is the structure most of the organic chemists like to use. So even though they also emphasize 9 of them by themselves can represent the real picture. But that will help you to predict a lot of those important reactions. For them, those sort of also para-directors. We have something like, yeah.
What in 3D isn't that all the same?
Huh?
In 3D, when you spin, it's all the same.
Yeah, they're all the same. And so therefore, Robinson, okay? The one organic chemistry is called Robinson. And Robinson is the first one who synthesized some of those, who observed some of the molecules from nature. And they said he's the first one who, by observing nature, and try to synthesize those from the nature.
Oh, like bioengineering?
Yeah, he synthesized some of those, okay.
It's okay.
Some of those amine, some of those, so some of those amine like molecules is kind of very important drugs. Right. So what does Robinson? Right? Robinson, and there's some very important name after him. So-called Robinson annihilation, which included many other processes, important reactions. He will just use this structure. And this structure, obviously, people say this is a better structure, and that, which means you don't really have a double bond, single bond. That's really representing the real, like those data, experimental data for bending. For bending, if you draw like this, that means you have a single bond, double bond. But then you will see like most of the organic teacher will tell you, never use that. Never use that. Always use those because that will tell you if I have some of those substituent on benzene, so if I put here a nitro group, and then that will tell you, so here this called the meta, this called this called the pair positions, and if you use those kind of double bond, single bond, you can figure out this has a little more electron density. If you use that, you can never figure out, what is the. All right. I think that the guy who wrote the book is a physical chemist. So he studied some of those quantum. So when you study those quantum chemistry, first emphasize those kind of structures. Yeah, he's the one who I know his background. He's a physical chemistry. Right. So how many of those resonance structures this NO2 magnetic has? 2? Yeah, very good. You draw the structure, okay? I think this will give you the idea. You will have those left over, and you put on the center, but the center still don't have orbital, right? So the middle is N, right? So you have 1 O and 1 O, right? So let's jump in one step. We make one connection. And then let's counting the total number of electrons. So this N give you 5. This 2O give you 12. This 1 give you one more. We see +1, that means become +1 charge, you have +1 electron. So altogether you have 18 electrons. Ready? Right, 18 electrons are our complete orbital, because the O need orbital. Right? Am I right? So now you complete the orbital for all the terminals. So what do you do? Take a break. Take a time out. Right? Take a time out, and then you see how many available. 18 available. How many on the structure? 16. Right? Okay. So you have a 16. You do a subtraction. You see you have a 2 left over. Now I think I repeating this step is I want to emphasize, if you have those left over, you put those left over on what atom? On the center. So on the center, so I will put it here. So either way, if you put on the center, you have a left over, or you don't have a left over, you still want to make sure if the center need orbital, give them orbital. And then, so right now, does the center has orbital? The center right now only has 3 pairs, right? So therefore, you can take 1 pair from the level, and together with that pair, and you have this structure. Okay? Or you take this from the other O, Get it? Right, so this is one structure, -1. This is another structure, -1. And this is our resonance. This is our resonance. I think we usually talk about those user resonance. If you want to argue with
So resonance is 2?
yeah, this is resonance too. All right, so I think what is this slide? What is the number? Yeah, so I think we're finish it here. Okay, so I think we are right in the middle. We have 100, right? And 100, and we are on 50. So we will come back next week. Tuesday, continue on this chapter. So more about the lab. The lab is we were like postpone the lab until we finish the chapter 10. That lab is kind of like what you said. It's very very simple lab. You can do it anytime, and you just pretty much draw the blue structure. And you have to finish chapter 10 because you need to know how to use the blue structure, pre-veterinary geometry, and polarity. And what is polar? And CO2 non-polar. How do you know that? So I will let you do the lab anytime. Okay, have a good scientific. Final? How many exams? Yeah, the next one is that. Oh, this is that. You can use this one
My sister made me some allergy. I don't see Is it get wet out, like I'm allergic to mold? And it's been warm, now it's gotten cold.
I'm off for the next 5 days. So maybe I'll stay over. Well, actually, I work tomorrow. Oh, it's only half day. Sorry.
So for like these, you're just supposed to like, go in that wavelength from the ones that we got and find the highest and the lowest.
Yeah, so in that range, first of
So
all,
none of them were in that range, but those.
yeah, I think that's only one.
Okay,
Pretty much this series is from any high level to the second one.
okay.
Right?
No, Ashley, wasn't here for the past 2 weeks, and she has all the data from the lab from 2 weeks ago, so what are we supposed to do?
You talk to her, maybe just, you can turn in the lab like later.